At points P1 and P2 we have charges Q1 and Q2. The distance between the charges is r. If the charges have the same sign, that is if both charges are positive or if both charges are negative, then the force on Q1 due to Q2 will be in a direction away from Q2. It will be in a direction along the line joining the two charges, but away from Q2. We could call it F12, the force on Q1 due to Q2. We could use an underline here, or we could use an arrow. Now, by Newton's third law, if there's a force on this charge due to Q2, then there must be a force on Q2 due to Q1. And the force on Q2 will have the same magnitude as this force here, but opposite direction. If vectors have the same magnitude but opposite direction, then one of the vectors is got by minusing the other vector. So F21 can be got by minusing F12. So this is Newton's third law. Suppose the charges have opposite sign. Suppose Q1 is positive and Q2 is negative, or Q2 is positive and Q1 is negative. Then there will be a force of attraction between the charges. So there will be a force on Q1 in this direction, along the line joining the charges. So this is F12, and by Newton's third law, if there's a force on charge 1 due to charge 2, there must be a force on charge 2 due to charge 1, which is the same magnitude but opposite direction. So this will be F21, force on 2 due to 1. Coulomb's law says that the magnitude of the force on this charge, Q1, is given by the magnitude of the product of the charges divided by the square of the distance between the charges. So as we know, Q1 or Q2 could be negative, so we have to take magnitudes here to ensure that this quantity is positive. We just want the magnitude of this vector. By the way, we could just write this as F12. F12 without an arrow also indicates the magnitude. So what this means is that if we double either of these charges, the charges are given in coulombs, then we double the force on each charge. So if we double Q1 or Q2, we double the force. If we double the distance between the charges, the magnitude of the force goes down by a factor of 4, because 2 squared is 4. If we triple the distance between the charges, then the force will decrease by a factor of 9. 3 squared is 9. Now the proportionality constant K is given by 1 over 4 pi epsilon 0, where epsilon 0 is this number here. Now I will revert to this notation for a vector. This is the notation that's used in the notes, the underline. So we are going to look at the vector F12. Here we just have the magnitude, and we are going to get this vector in terms of a unit vector that's along the direction of the line joining the two charges. Now I've put the unit vector R at Q2, but of course I could have shown it at the other charge. I could have shown it here. So, well, these would be two different vectors, but it doesn't matter which way we describe F12. Now, if R is our unit vector, then the vector F12 is given by this here, and we are going to check that this makes sense. Let's consider the case where the charges are opposite. So let's suppose that we have a negative charge Q1 and we have a positive charge Q2. Then what do we get for this quantity? What sign will this quantity have? Well, if Q1 is negative and Q2 is positive, then we have negative times positive, which is negative. R squared is always positive, that's just the distance, and the constant K is always positive. So then F12 will be a negative scalar times unit vector R. If we have a negative scalar times a vector, we reverse the direction of the vector. So the direction of F12 will be opposite. So in general, F12 is a scalar multiple of unit vector R. So vector F12 is along the line joining the two charges, along the same line that contains unit vector R, of course. Now if we reverse these charges, if say Q1 is positive and Q2 is negative, then of course we'll have the same situation. We will have a force of attraction between the charges. So F12 will be in the direction shown here. So these two cases essentially give us the same direction for F12. The next case, of course, is the situation where both charges are positive or both charges are negative. If both charges are positive, then this quantity will be positive. So vector F12 will be in the same direction as vector R. It will be a positive scalar multiple of vector R. So F12 will be in this direction. So the charges will repel each other. And the same is true if both charges are negative. Negative times negative gives positive. The magnitude of the force will be in newtons. So we must have the charges in coulombs, the distance between them in meters, and the constant k has to be given by this quantity here, 1 over 4 pi epsilon 0, where epsilon 0 has this value. Let's consider this situation here. As before, we have a charge q1 at the point p1. But now, at this point, which I'm calling G, we have a second charge q2, whose value we know, and whose value is actually plus 1 coulombs. We can write C for coulombs if we like. Now this time I'm showing the unit vector R pointing towards the point G. So it has a magnitude of 1, of course, but I've just reversed this direction for convenience. Well, you don't have to, but it's just I want to be consistent with what's in the notes. It turns out that we can write F21, that is the force on charge Q2 due to Q1, like this here. We will check that this is correct. Before we do that, Q2 is plus 1, so we can plug plus 1 in for Q2. So we're multiplying Q1 by plus 1, so same as before, Coulomb's law again. But of course if we multiply Q1 by plus 1, we just get Q1. Now we need to check that this makes sense. Let's suppose that Q1 is positive. So this is a positive charge. Well then, the force on Q2 will be away from Q1, so it should be in this direction. It should be in the same direction as unit vector R, and indeed it is. If Q1 is positive, then this thing will be positive. So we'll have a positive scalar multiplied by unit vector R. So F21 will be in the same direction as unit vector R. So we'll have a repulsive force. Of course, if we swap that around, if Q1 is negative, then you know it's pretty clear that this is going to be negative. So F21 will be a negative scalar multiple of unit vector R. So F21 will point in a direction that's opposite to unit vector R. So we'll have an attractive force. Now, this force is given a special name. The force on a unit positive charge is known as the electric field at this point. So we use the letter E to denote the electric field vector. And the 2,1 indicates we're dealing with the electric field at this point. We could call it 2, or we could write G here, I suppose, at this point due to this point here, P1 or 1. So the electric field vector is entirely due to this single charge Q1. Now, since the unit of the force vector is newtons, well, we've divided this by coulombs. So the unit of this quantity would be newtons per coulomb, because we divided, remember, by the charge Q2. That's one way to get rid of Q2. If Q2 was not plus 1, we would just divide this by the charge. So newtons per coulomb, NC to the power minus 1. So this is the unit of the electric field. Now we can imagine several other charges apart from Q1. We could imagine a charge Q2 at P2, a charge Q3 at point P3, and so on. So here's the second charge Q2, and we would have a force on the unit positive charge due to Q2. Well, I better give this a different name. I can't call it Q2. So we have an electric field vector due to Q1, which I could call E1, I suppose. Well, I suppose I could say the electric field at G due to 1, but I leave out the G. When E here refers to the electric field at G. Of course, E will vary depending on what point we're talking about, but let's assume we're just talking about this point. we have another electric field vector due to this charge Q2. The direction of this electric field vector will be along the line joining this point with the point G. If Q2 is positive, then the electric field vector will be along this direction. If Q2 is negative, then the electric field vector will be along this direction. So we can call this electric field vector E2, the electric field at G due to Q2. Now, since we're going to have lots of different distances involved here, we will call this distance here R1, the distance of Q1 to the unit positive charge, and then this will be unit vector R1. So here's the electric field at this point due to charge Q1, and at E2 we have different value here because R2 is the distance of Q2 to the charge at G, and here is unit vector R2. So we're defining unit vector R2 to be pointing from the charges towards the point G. We could imagine yet another charge Q3 and the electric field at G due to Q3. Again, if Q3 is positive, then the electric field will be in this direction, pointing away from Q3 and along the line joining Q3 to the point G. And we can call this electric field E3. That's assuming that Q3 is positive. If Q3 is negative, of course, E3 will be in this direction. So vector E3 is given by K times Q1 over R3 squared times unit vector R3. So how would we get the electric field at this point due to the three charges Q1, Q2 and Q3? Well, we just get the vector sum of E1, E2 and E3. I am calling the resultant of these three electric field vectors at G E sub G. Of course, we can imagine extending this result to yet more charges. We could have a fourth charge Q4 and Q5 and so on. Next, we will write the unit vectors in a different form. We just go back to the definition of, say, unit vector R1, this vector here. Well, that's just the vector R1 whose tail is at Q1 and whose head is at the point G. So this green vector is R1. Its magnitude is just R1 without the underline. And what do we do with that vector? Well, we divide by its magnitude. We could show its magnitude like that, or we could just show R1 without the underline. So this is just a definition of a unit vector. To show that this definition works, we could just take the magnitudes. So if we take the magnitude of this, well, it's just the same as the magnitude of this, of course. So it's the magnitude of R1, the magnitude of what's on top, divided by the magnitude of what's underneath. Well, what's underneath is positive. It is a magnitude, so the magnitude of the distance is just R1. But of course, that's the same as what's on top. The magnitude of vector R1 is just R1. We can write it like this. So we have R1 divided by R1, which is 1. So we can write this in two different ways. So that makes sense. We want the magnitude of the unit vector to come out to equal 1. So anyway, we will use this form and plug it in here. So plug in R1, vector R1 over R1 in here. And of course we have R1 squared times R1. So we're going to get an R1 cubed. So now we've gotten rid of this. So now we have vector E1 in terms of vector R1 rather than in terms of the unit vector R1 hat. And of course we can do exactly the same here. We just replace the 2 with a 1, or the 1 with a 2 I mean, sorry. And of course we're going to get R2 squared by R2 here, so we're going to end up with R2 cubed here, and we're going to have not unit vector R2 but vector R2. Vector R2 is the vector whose tail is at the point Q2 and whose head is at the point G. And then similarly, of course, for charge Q3,